Hey Freddie, how's it going?
Going all right. How are you doing?
Doing all right. Doing all right. It's that time of the season again where students are asking about their grades. So that's fun to give lengthy responses in emails, and it seems like they don't read any of it. So
I've, man, I don't know if it's like calculus. It's probably like that plus like getting kind of lucky, but I have not had what was the term you used for it? I think during our meeting last week is like grade grubbing or something. Was
yeah,
that what it is?
not all of them were like that. More of them were just
Is
stressed
that the term you used though? Grade grubbing?
for a
I
different
hadn't heard that before.
that term. Yep, yep, yep. I was
Yeah, okay.
like thinking was a mountain out of a molehill. I think it's what the
Oh, okay. Yeah, I haven't had a lot of that this semester. Maybe I will after this test because I'm gonna probably make it harder than their first one was. But
hmm When's the exam?
I got one on Tuesday.
Nice. I got one Monday. Should be fun. Yeah.
It's that time.
Yep. Yep.
Hey, Marcellus, congrats.
Yeah. Congrats, Mazelis. You're a free man.
How was the remainder?
Oh, you mean like the question part?
Yeah, yeah.
They didn't really ask any questions. I think it was mostly suggestion part, like things I could do afterwards.
Uh-huh.
I got
Cool.
some nice ideas, but I'm still waiting for their emails because they said they would send me an email with references.
I see.
But
Nice.
All right, hello everyone.
Hello.
Hello. Welcome back. Anybody have any questions or anything? No? So we will resume the problem sessions in the usual manner on Friday. I think Tyler told us that he wants to do some Galois theory stuff, profinite Galois theory, which is fine. I think I'm a little behind in terms of uploading problems to the PDF file, but probably not as far behind as many of you are in solving problems. So maybe it works out. Yeah, anyway. Okay, well, I mean, if there are no questions, I'd kind of like to get on with it. I think at the end of the last lecture, I kind of got a little bit, I don't know, impatient / excited / tired or something, and just kind of spewed out a bunch of things. And I was like, oh, who has time to say these things carefully? Well, sure we do. So, you know, whatever I was planning on, you know, speeding through, it should not be the local class field theory part of the course, right? So, yeah, so I just want to go over. Not really a review, but there were just a bunch of things that I kind of said out of the side of my mouth, and so we want to prove some further properties of this reciprocity map, and then we'll sort of get to a point where the remaining result is this existence theorem, and we'll sort of understand very precisely what remains to be done. It's actually some statement about the intersection of all the subgroups of the unit group of our local field that arise as the norm from a finite abelian extension. So we sort of, in fact, we want to know that the intersection of all those subgroups is trivial. Okay, so let's get back into it. Yeah. So as until further notice, you know, K is a local field, which in our course, remember, means a complete discretely valued field with finite residue field. I don't know why it occurred to me just now to say this, but that can be extended slightly. There's a notion of a quasi-finite field, which is sort of something that Galois theoretically looks like a finite field. So if its absolute Galois group is isomorphic to Z hat and has a canonical generator, then you could do class field theory for a local field with quasi-finite residue field, and that's what Sayre does in his local fields. I must say I can't think of any. It's always nice to generalize something important, no matter how modestly, but I can't think of any real payoff for doing that. Okay, So, right, so we defined, one of our main results is that, let's just stick to finite abelian extensions now. The Tate-Nakayama stuff gave us a canonical isomorphism from K star mod the norm of L star for any finite abelian extension to the automorphism group of the extension. So in particular, the index of the norm of any finite abelian extension of our local field K is, well, the size of the Galois group, which is the degree of L over K. Yeah, again, so that came from some, this thing is like an H0 in Tate cohomology. And then this thing was, in general, in fact, it was the abelianization of something, which is an H-2 in Tate cohomology. And so this map was the inverse of some map that we got by cupping with our fundamental class, which was our magic cohomology class in degree 2 that we essentially our class in the Brouwer group that we got by really understanding what was happening in the Brouwer group. Okay, so again, there's always bookkeeping here. I mean, these maps are sort of like, you know, we are giving in principle pretty explicit descriptions of, explicit isn't the right word, but we're giving, you know, canonical kind of, you know, clean descriptions of a lot of these maps, but then, you know, if you string 3 canonical isomorphisms together and take an inverse, then if you want to do something with it, then, you know, you have to track that. That will actually come up in one of the first things. Okay, so our main goal is to show that this map omega, this reciprocity map. Oh, so I didn't say. So that was defined at any finite level, and then we had this result, the proof of which I found possibly had a small gap in it, but we moved on. I mean, the result is true. Just talking about Harari's presentation. So not only did we have these isomorphisms, but these isomorphisms were functorial. There we go. This diagram commutes. If you have one finite Galois extension contained in another, then you have a canonical inverse system on this side, just coming by taking the quotient. The norms from a bigger field are going to be a smaller group. That's just basic field theory. And then we have a canonical inverse system on this side, just coming from just coming from the Galois theory of it. And so this corollary was stating that these isomorphisms are compatible with the restriction maps in this inverse system, and so therefore they induce an isomorphism of profinite groups upon taking the inverse limit. Okay, and so our goal is to show that omega is a profinite completion map of the topological group K star. So again, what is a profinite completion map of a topological group? Well, it's universal for maps from that topological group into a profinite group. Okay, and so in particular, that would make the maximal abelian extension of K the profinite completion of the unit group. And again, so I said this last time, I might as well say it a little bit better. It's not very mysterious at all what the profinite completion of K star is. It happens not to be profinite, but in a like, okay, it's not profinite, that sounds bad, it's not bad. It's totally understandable in what manner it fails to be profinite. So namely, if you just, what is happening here, if you just take the profinite completion of, so again, profinite completion is a functor. So if you take the profinite completion of the valuation map, then that gives you a map from the profinite completion of K star to the profinite completion of Z. That's basically what we have to do. And then the kernel of that map is going to be the unit group, which is already profinitely complete. So we have this canonical short exact sequence. The unit group is going to sit inside the profinite completion, and then via the profinite completion of the valuation map, it's going to surject onto Z hat. Whereas if I took this hat away, I should also take this hat away. So that's the only thing that's happening. when we profinite complete. And so here's something where, again, I said this very quickly last time, but let me just say it more nicely. So a profinite group is projective. It's kind of what it's a very analogous to the notion of a projective object in a Abelian category, although this is not an Abelian category. So for any continuous surjection from a profinite group onto your group P, projectivity means that there's a section. Okay, so you have a continuous homomorphism, so that if you know, so that you have this section condition, so a one-sided inverse. Right, and so then as usual, projective means that whenever you have a short exact sequence of profinite groups terminating at your projective guy, then the section gives you a splitting of that short exact sequence, but we're working with commutative groups, lucky us. But as far as the definition is concerned, I didn't say the groups were commutative. So what is a split short exact sequence of not necessarily commutative groups? That means that you get a semi-direct product decomposition, right? So the K is normal, and then you're wondering if you have some, what am I asking? I'm asking, do I have some subgroup of G that projects, that under this quotient map, it gets mapped isomorphically to P under the projection map, right? So that gives me a copy of P inside G, from which I can build G as the semi-direct product. Okay, so a profinite group is projective if every short exact sequence terminating with the group splits. And then of course, well, if G is commutative, then semi-direct products have to be direct products. And so yeah, so in particular, if you have a projective profinite group and your group is commutative, then the sequence splits. Okay, so first let me just tell you a result about which profinite groups are projective. I think this theorem, I know this theorem from Serre's Galois cohomology. It may actually be due to Serre. My two guesses are Serre and Tate. So for a profinite group G, being projective is equivalent to cohomological dimension at most 1. Okay. And so that's nice because, of course, we've been studying groups of cohomological dimension at most 1. In particular, we know that Z hat is a group of cohomological dimension 1. We don't need it, and I haven't defined it completely, but this is kind of interesting because this is what do we know about discrete groups that have cohomological dimension at most 1? It's easy to prove using topology that every free group has cohomological dimension at most 1. And it's quite a deep theorem, Stallings and maybe Serre and such people, that the converse is also true, that the discrete groups of cohomological dimension 1 are precisely the non-trivial free groups. And so you might ask, well, you know, is there a connection to free groups? And again, for the theory of cohomological dimension of profinite groups, everything kind of gets shoved through the Sylow theory of pro-P groups, right? So the cohomological dimension of G is at most 1, if and only if the cohomological dimension of each of its Sylow P subgroups is at most 1. And so really you should be asking, well, what does it mean for a pro-P group to be of cohomological dimension at most 1, or what does it mean for a pro-P group to be projective? And it turns out that at that level, you get the analog of this Stallings theorem. So a pro-P group is of cohomological dimension at most 1, if and only if it's a free pro-P group. Well, sorry, I'm not defining what a free pro-P group is, but if it were, this is a tricky definition if the group is not finitely generated, but if you have a, for instance, if you take a finitely generated free group, okay, so the free group on some finite number of generators, and then you take its pro-P completion, okay, so that's like profinite completion, only all the finite quotients have to be P groups, then that is what a finitely generated free pro-P group is. It's the pro-P completion of a finitely generated profinite group. And then infinitely generated free pro-P group is kind of a tricky definition, and now it's really not going to come up in what we're doing. Anyway, so projective is the same as cohomological dimension at most 1. And so lucky for us, well, we proved that Z hat has cohomological dimension at most 1. It's also true that the CeeLo P subgroup of Z hat is ZP, and yep, ZP is the pro P completion of Z, which is the free group of rank 1. So even what I just told you actually gives you another way of showing that Z hat has cohomological dimension at most 1. So anyway, so therefore this sequence that I told you about certainly splits. And so as I said, the profinite completion of the unit group of the field is certainly just obtained by, is just the direct product of the unit group with Z hat. This is ridiculous overkill for this, because of course, we already know that the unit group of K star is isomorphic to UK across Z. We have the same map before profinite completions, and Z is a free Z module, so that sequence splits for the same reason. And certainly, by the way, it's certainly true that profinite completion commutes with at least finite direct products. So that was really overkill, but what's not overkill necessarily is the same statement on the Galois group side, right? So now if I go on the Galois group side, I'm trying to understand the maximal abelian extension of K, right? That's what class field theory is supposed to be doing. And there's certainly a piece of it, more precisely a quotient of it, that I understand perfectly. Namely, I understand the Galois group of the maximal unramified extension of K, because again, under reduction modulo of the maximal ideal, that's canonically isomorphic to the absolute Galois group of the finite residue field. Okay. So I have a short exact sequence of profinite groups terminating at Z hat. Okay, so it's the same as before, but now, now I'm in a position to say, hey, because Z hat is a projective profinite group, and because it's got an ab on it, so I'm pretty sure it's commutative, therefore the maximal abelian extension of K does split as the direct product of Z hat and this inertia group. Okay, so again, I said this last time, but I'm saying it better this time. And so if you like, so what am I really saying? I'm saying that the abelian inertia group, it's also true if you don't take the abelianization as a semi-direct product, by the way, right? If I just removed all these abs, then I've kind of said nothing. And so the same thing would be true, except I would have a semi-direct product. Maybe I should write that down. So also GK is isomorphic to the full inertia group, semi-direct, and that is this is an actual non-trivial semi-direct product. Okay, as is talked about in my number theory 2 notes. Okay, so what am I saying? I'm saying that not only is this IK or IK ab, not only is it the Galois group of an extension of K on RAM, there's also an extension of K that sort of base changes to, yeah, maybe that, I won't write it, but maybe that's the way I'll say it. So what I'm saying is there's some extension L of K that when you base change to K on RAM gives you this extension. So there's some totally ramified extension of K, which is sort of complementary to this totally unramified extension here. Okay. Anyway, so right. So in other words, kind of most of it is this piece, is what I'm saying. We understand the Mac. We didn't need class field theory to understand the maximal unramified extension. We understand the maximal unramified extension of every complete discretely valued field. Okay. Right, and so my claim is that this reciprocity map is inducing an isomorphism between these two split exact sequences. Okay, so we have okay, I want to say more words, but that's exactly what I want. Okay, so I have this, right? So we have the reciprocity map is giving us. I claim that this is giving us an isomorphism on the profinite completion. We don't know it's injective yet. We only know that it's surjective. So we're trying to show that the kernel is 0. Yeah, and so the question is to see that we get this isomorphism. Okay. Right, but actually, I'm going to show you right now that the reciprocity map induces that the reciprocity map restricted to the unit group gives you the abelian inertia group. Okay, so I will prove that. Again, after everything I do today, we'll basically be done with the local class field theory, at least in terms of the main statements that we want, except for showing that this map is injective. That's called the existence theory. Okay. So yeah, so for the step one, now this is a result that I mentioned quickly last time, and I was like, oh, who has time to prove these things? Well, today we do. So if I have a finite unramified extension, again, the reciprocity map nothing should be scary for unramified extensions. Well, certainly it's abelian, it's cyclic. It has a canonical generator. The canonical generator is, whatever maps to the Q power Frobenius map in the isomorphism to the extension of residue fields. I mean, these are the Frobenius maps. These are the Frobenius elements that you hear about in algebraic number theory, now given as elements of local fields, but that's really where they come from anyway. That's a local fields way of saying it. You could then you say the Galois group of the completion is identified with the decomposition group in the global case. That's the local global compatibility. Probably surely that will come up at the end of the course if we get that far. Anyway, so this is what the reciprocity map is. So odd L over K is a cyclic group of order the degree of L over K, canonically generated by F. So the reciprocity map is a map from K star mod norm of L isomorphically into that group. So to tell me what the reciprocity map is on every element of K star, you have to tell me which power of F it maps to. And it's pretty nice. It just maps to the power is given by the valuation. Okay, so that's the statement. And this is really, there's kind of no new ideas here. You just have to kind of keep your head and track through. So first of all, it's enough to show this, as usual for the duality theory of finite commutative groups. It's enough to show that this is true after applying an arbitrary character. Again, that's just how character theory of finite groups works. Two elements of a finite commutative group are equal if and only if they're equal after applying every character. That's undergraduate level fact. Okay, so I take a character of this automorphism group and I want to show that it's true after I apply a character. And okay, a character is a homomorphism, so evidently the character of some power of the Frobenius is, since the character takes values in Q mod Z, that's what we mean by characters, which is additive. There's like a multiplicative to additive thing going on. Then the right-hand side, when I apply a character, is certainly the integer v of x times whatever the character value on the canonical generator was. Okay. The key is this identity, which we worked for. This kind of slightly scary looking identity is really helping us here. So we know this. And so therefore, I just want to show that the right-hand side is equal to v of x times chi of f. Okay. So now we have to remember what the invariant map is. The invariant map was started with the Brouwer group of L over K. Okay, so that's this thing. Then all of these maps are isomorphisms, so we showed. Then you go from L star to Z, essentially by taking the valuation map, the upstairs valuation map. So I'm being somewhat, which I denoted this by some Greek letter last time. I can't remember. To be really precise, it's just the induced map on cohomology from the G equivariant valuation map going from L star. Okay, that was the first map. Then we had this delta inverse, which is great. This delta inverse is literally the inverse of D. So again, I don't know why sometimes I write D and sometimes I write delta here. Let's write delta. Harari is worse. Harari decides after a certain point to write chi instead of delta chi. I found that slightly confusing. Anyway, so the delta inverse is the delta inverse, but the usual z goes to q mod z. So it's the inverse there. That takes us into, this is literally the character group of the Galois group of the abelian extension. And so how do I get from characters, Q mod Z valued characters to Q mod Z? Well, I better evaluate my character somewhere, and thank goodness I have a canonical generator to evaluate on. Okay. And okay, you gotta just think that how it all works. So what is this X cup d chi? I claim that in some sense it's X tensor d chi. This is a cup product with an element in H0. So it really is just the induced map in cohomology of the tensor product map. Okay. So I claim, where does that bring me to? That brings me to the first element here. That's what this Brouwer element is. Okay. And then now what am I doing? Now, again, I have this two cocycle with values in L star, and then I'm just applying the valuation map to get me into Z. Okay. And so I claim if you think this through a little bit, so the d chi has an H2, is an element of H2 with values in Z. And so what is this tensor product followed by this map doing? So I claim that it is just the same. You do this, and the sense of this multiplication after you apply this map, it just gives you it just becomes I mean, in a sense, I have what's my tensor product? My tensor product is Z tensored over Z with L cross. And so the map Z tensored over Z with L cross is isomorphic to L cross, and the isomorphism is essentially multiplication. Okay, if you want to really buy this, you gotta do it yourself, but I'm trying to show you, how it goes. Okay, so under this map, I claim this goes to just multiplication V of X times D chi. Okay, what's delta inverse? Delta inverse is exactly what delta inverse of delta of X is X. You heard it here first. It's a group homomorphism. That's an integer, so it goes to V of X times chi. And then, I guess, well, depending upon, I guess are we writing characters additively or multiplicatively? I guess we're writing them, at the moment, it looks like I'm writing them additively. Fine. Okay, so it goes to V of X times chi, and then I evaluated F, and I indeed get V of X times chi of F, which is what I wanted to get. Okay. So yeah, and so this was supposed to, I mean, this is more detail than Harari gives, by the way. He just says it follows easily from blah, 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 blah. But okay, this is an important formula. This is saying we know what the reciprocity map is doing on an unramified extension. Okay. In particular, we can see that the kernel of this map is what it what it should be, right? So the kernel here, so when is this going to map to 0? The kernel is going to be the elements whose valuation is divisible by the degree of the extension. What does that mean? That means that the norm on, yeah, maybe I should write that down. So corollary, if L over K is unramified of degree n, then I've told you exactly what the norm is. So the norms from L are precisely equal to the elements in K such that the valuation is divisible. Oops, V is a terrible name for an element. X in K such that the valuation of X is divisible by. In particular, this contains the unit group of K. Okay, so I'm kind of trying to figure out what these norm subgroups are. Have no fear what the norm subgroup is for a finite degree unramified extension. It's just this. All it does is impose the condition that the valuation should be divisible by n, which clearly gives you an index out subgroup. Okay. As you can see, it's kind of more interesting what's happening on the unit group side. Okay, so now I want to show that the reciprocity map applied to the unit group is the abelianized inertia group. Right, so I claim that. And it's enough to show this, everything is obtained by passing to the inverse limit, so it's enough to show this at every finite level. So if I have a finite abelian extension L over K, let me write K prime for the maximal unramified sub-extension of L over K, and let's suppose that K prime over K has degree F is a better name for that. That's what we usually call that. Let's call it F, right? It's literally the residual, therefore we would call the degree of that E. Yeah, that's how it works. Okay, and so what do I want to show? So I want to show that, right, so for any that I want to show that the image of the unit group is equal to the inertia group of this extension. Okay, great. Okay. Yeah, so if you show that at every finite level, then, you know, then therefore in the inverse, the map is sort of defined on K star into the inverse limit. So if at every finite level, its image is the inertia subgroup at that finite level, then you take the inverse limit of all the finite level inertia groups, and that is the of the abelian extensions, and that is the abelianized inertia group. Okay. So this is actually not so bad. So first of all, if X is a unit, then by what we just proved, if you take the reciprocity map on the unramified subextension, well, then you're trivial. Okay. And so this, I mean, again, I just wrote down a slightly stronger version of this, but so certainly, certainly the units are in the kernel of the reciprocity map on every unramified extension. Okay. And so what did that tell me? If the reciprocity map, so the reciprocity map at level K prime is trivial on the units, right? But we're doing an inverse limit. So basically I'm trying to understand if I'm trying to understand the L over K reciprocity map, then it lands in the entire group. I'm saying if it lands in the entire group, let me look at its image in the unramified quotient. Well, if the image in the unramified quotient was trivial, well, if the image in the quotient was trivial, then it lay in the kernel. Okay, so that little computation tells me that the unit group certainly maps into the inertia group. So now I just need the other way around. Now I need to take any element of the inertia group and actually show that it's a norm. Okay, and that's not so bad either. So I take a sigma in the inertia group. The reciprocity map is surjective at every finite level. So great. So give me an A in K star so that the reciprocity map of A is equal to whatever group element I want. It's you know, some isomorphism after you mod out by the norm, so it's surjective. I'm converting my D's to F's. F. Okay. And so, yeah, but what we just said, again, this is, I just clarified this, that because you're in the kernel of the unramified reciprocity map, if and only if your valuation is divisible by the degree of by the residual degree. So yes, by what I just said, the valuation, any such element that maps into the inertia group, it's under the reciprocity map, its valuation has to be divisible by F. Let me take advantage of that. Therefore, I can choose an upstairs element whose upstairs valuation is equal to the valuation, the K valuation of A divided by F. All I'm saying is that, you know, the VK of A is divisible by F. So great. So there's some integer, which is, so VK over F is an integer. Every integer is the valuation of some element of L. Okay. And then now we have this, you know, just how does the valuation compare with the norm, which I've recalled before. If you take the norm in any finite extension of local fields, if you take the norm of an upstairs element and then take the downstairs valuation, that's very closely related to the upstairs valuation of the original element, but they differ by their residual degree. Okay. Again, you just don't need to remember this, but you look back at the definition of the norm and you get it. Okay, and so then the norm is V times F times VL of B, which as you can see is VK of A. So what? Therefore, I have two elements, norm of B and A, that have the same valuation. So therefore, their ratio has valuation 0, and there is a unit. So U is the difference of these two guys, is a unit in K, and sigma, which by the arbitrary inertia element, which by definition was the reciprocity map applied to A, well, I'm saying it's also the reciprocity map applied to U. Why is that true? Well, A and U differ by a norm, and yup, the norm is the kernel of the reciprocity map. Okay, so for sure, the reciprocity map of anything is equal to the reciprocity map of anything adjusted by a norm, and we're done. So what did I do? I took an arbitrary element of the inertia group and showed that it was in the image of the reciprocity map. Okay. And so again, so I've done this at every finite level, right? So for every finite level, I've shown that the reciprocity map L over K maps the image of UK, the unit group under the finite level reciprocity map, is the inertia group of the finite abelian extension. And you think about this for a couple seconds, and it passes to the inverse limit and tells you what I said. Okay. So you see, so now I've shown, I still don't know that this map is, I've kind of shown this exact sequence, except for the, I mean, if I erase this, then I've actually shown this at this point. I just want this map to be an injection, and therefore its restriction will also be, I know that this map is a surjection, and I know that this map is a surjection. And so just as soon as I know that this map is an injection, then I'll know that its restriction is an injection as well. And that's local class field theory. I mean, we could touch it up in various ways, but that's the main part of it. Okay. Any questions about that? We're making progress. Yeah, this was very important, by the way. So you know, in terms of like understanding the difference between the unramified extensions and the ramified extensions. Okay. All right. So now for the rest of the lecture, maybe even a little bit more. We'll see how far we get. I just want to do kind of some bookkeeping here. So this a little bit of kind of developing the Galois correspondence a little bit here. So okay, first proposition. If L over K is a finite abelian extension of my local field, then the norm group is an open finite index subgroup of K star. I mean, by the way, maybe we should stop right here. Haven't we shown this already? Well, we certainly know its finite index. We know its index is equal to the degree of L over K. So the only thing I'm really asserting here is that it's open. Okay. And that will be kind of obvious in characteristic 0 and not obvious in positive characteristic. So, but we'll prove it. And then the next thing, so this I actually mentioned last time out of the side of my mouth, and now I'll prove it. Moreover, the norm subgroups associated to distinct finite abelian extensions are different. Okay, sounds good. Okay, so let's prove it. So as I said, for sure, the norm of a finite abelian extension, the image of the norms, has index equal to the degree of the extension. That was what Tate Nakayama bought us. So it has finite index. Why is it open? Well, there's kind of two strategies here. If K is p-adic, by the way, every finite index subgroup of the multiplicative group of K star is open. So if we can show that, we go home early, right? It's better to show that, right? So let me remind you why that's true. So for the second time in this lecture, K star is isomorphic to the unit group across Z, and by p-adic Lie theory, we saw a couple lectures ago that UK is isomorphic to some number of copies. We know what number of copies of ZP cross a finite group, okay? And in particular, this is a topologically finitely generated profinite group, and by this enormous theorem that I told you about, crap, at the moment I'm forgetting the two people who proved it, it's like 20 years ago or so, every finite index subgroup of a topologically finitely generated profinite group is open, but that's ridiculous overkill if you just think about if you just think about this particular finite group, you will convince yourself that every finite index subgroup is open. I mean, one way to say it is that this group is obviously the profinite completion of a certain discrete group, and then that gives two. Okay. Or the pro-p completion, whatever. Yeah. Anyway, you can see it that way. Okay, so we know that every subgroup of the unit group is open, and then we're just going from the unit group to the unit group across Z. Is that any trouble? No, it isn't. So for instance, let me take my subgroup of the unit group of K. Let's suppose it has finite index n. So if if you're a commutative group, then if you have index n, then the quotient group has exponent n. If I take any element of the quotient and I multiply it by n, well, if I got a finite abelian group of order n, n must kill every element in that group. And so therefore, H has to contain k star to the n, which is uk to the n cross nz. And okay, uk to the n, as we talked about, is a finite index subgroup of uk, so it's open, and z is a discrete group, so everything is open, and so this subgroup is visibly an open subgroup of k cross. And then whenever, for any topological group, if you have a subgroup that contains a smaller open group, then you are yourself open. Okay, so that's the point. It's really not so hard to see that in the characteristic 0 case, every finite index subgroup of K star is open. Again, it's really not true in positive characteristics, so we better do something else. Yeah, so not every finite index subgroup is open, so we actually need to do something to show that the norm subgroups are open. I like this argument, but it made me feel bad because it uses some general topology facts, and I've been working really hard on my general topology notes, and these facts are still not in there. But here we go. So consider the norm map. Can't argue with that. It is certainly a continuous homomorphism. Why is that? I think I forgot and I wrote that down later. The norm map is a polynomial in the as I said, if you introduce a basis for L over K, then you can easily convince yourself that in the basis elements, the norm map is a homogeneous polynomial of degree n in n variables. Okay, so any polynomial is continuous. Any polynomial map on topological fields is continuous. So of course it's continuous. It's a continuous homomorphism of locally compact groups. What's the crux of it? I want to show that this map is a closed map, meaning of course that it takes closed subsets to closed subsets. If that's true, well then in particular its image is closed. But again, I already know that the image is a finite index subgroup. And as we mentioned long ago, open subgroups are precisely the, well, no, in any topological group, if you're closed and you have finite index, then you are also open. Because the complement is a finite union of cosets. So if you're closed, each of the cosets is closed. The complement is a finite union of closed things, so it's still closed. So the complement is closed, so you're open. Okay, now comes the interesting part. I'm going to talk about proper maps in the topological sense. So a continuous map between topological spaces is said to be proper if something which is pretty close to being universally closed from scheme theory. So this is kind of funny. If you're like, hey, why the hell are we calling these morphisms of schemes proper maps? In general topology, this definition is taken from Bourbaki general topology, as are the two results coming. So a map is proper if it's continuous, and whenever you take the direct product with any topological space whatsoever, so you have a natural map, the map is just f in the first coordinate and the identity in the second coordinate. then that map is closed. Okay, and that's very close to the and to being a complete analogy with the map and scheme theory. Notice though that like I could have tried to take a fiber product here, and I'm not taking a fiber, which that fiber products make sense in topology, but I'm not taking a fiber product. I'm just taking an ordinary Cartesian product. If the point of this lecture was to develop the topological theory of proper maps, I could probably take fiber products as well, but I'll just go with it. Okay. So yes, I'm just going to give you a couple of useful results. By the way, Harari refers back to Bourbaki. He doesn't really say what the results are. You have to look them up. I did. Here's what they are. So if you have a continuous, if you have a continuous map between topological spaces, Bourbaki proves this. It is proper in this sort of scheme theoretic looking sense if and only if it's closed and the fibers are quasi-compact. Okay. So that's kind of useful. Okay, so that's another notion of somehow this is like a compact morphism is one way of trying to think about it. But anyway, closed is what I wanted to hear, right? So I'm trying to show that my norm map is closed. So according to this first result of Bourbaki, it would certainly be enough to show that it's proper. Okay, but do I really want to show this? That looks ridiculous. So luckily, there's another result from Bourbaki. If things are much better if your maps are between locally compact spaces, which is not hard to believe, and luckily our norm map is a map between locally compact spaces. In that case, proper is equivalent to what other kinds of topologists might call a proper map. So if you were studying manifold topology, you may have heard the notion of a proper map between manifolds or something. And that's a map where the pre-image of any compact subset is again compact. So if you're studying maps between non-compact manifolds, then proper is kind of a nice condition on the map. Okay, what's the point of all this? According to Bourbaki, now all I need to show is that the pre-image of a compact subset is compact. If that's true, then it's proper. And if it's proper, then it's closed, and I really wanted it to be closed. Okay, that's not hard to show. Okay, and then moreover, everything is Hausdorff, so it's enough to show. Okay, so it's enough. This is what I'm trying to show. I'm trying to show that if I have a compact subset of K star, then its pre-image under the norm map is compact. In particular, everything is Hausdorff. So if A is compact, then it's closed. So its pre-image is certainly closed. So it would be fine to show that the pre-image is contained in a compact set, because if you're closed and contained in a compact set, then you're compact. Okay, so basically, if you give me some compact subset of K star, I just need to find some compact subset of L, which contains the pre-image of the compact subset of K star under the norm map, and that is really not that bad. Maybe I'm having more fun than I should here, but it's gonna end soon. Okay, so one more time, let's let what? V equals F L over K? No, it isn't. F equals F of L over K, just the residual degree, same thing it was before, same equation as we had before. Okay, exact same equation. What does this equation show? This equation shows in particular that the pre-image of anything which norms down to a unit was already a unit. So the unit group is compact, and so that already shows that the pre-image of the downstairs unit group is compact, and then we can reduce down to this. So now it's gonna follow easily. I will not give you the full details. I'm not skipping much. It follows that the pre-image of any coset of the unit group downstairs is compact. Well, maybe it's empty, but okay, the empty set is compact. If not, then how does the pre-image of a coset work? The non-empty pre-image of a coset is going to be kind of a coset of the pre-image. And so if I take an element y whose norm lies in the coset, then I promise that the pre-image of the coset xuk is actually y times the preimage of that subgroup. So in fact, the preimage of a coset is going to be a coset of the preimage. Okay, you can check that. And that's great because I just proved that the preimage of the unit group is compact, and certainly a translation is a homeomorphism. So that means that this guy is compact. Okay, so now I know that the preimage of any coset of UK is compact. And if I have an arbitrary compact space, then for each point in A, I have like that element X in A is contained in the coset XUK. That's open. UK is a compact open subgroup. And then by the miracle of compactness, I just gave you an infinite cover. You cover A by the corresponding cosets of this open subgroup, but it's compact, I'm assuming. So therefore, it's contained in a finite cover. And then we're done. Because if that's true, then the preimage of A is contained in the finite union of these guys. And so now it's contained in a finite union of compact spaces, which is again compact. Okay, so I just showed that for any compact subset of K star, its preimage is closed, of course, and contained in a compact set, so it's compact. Okay. Yeah, I kind of missed topology a little bit, so that was fun. Anyway, so yeah, so now we proved that all norm, even in positive characteristic, where not every finite index subgroup of K star is open, the norms are still open. Okay, so the next one is kind of Galois theory. This is pretty easy. So now I want to show that if I have two different finite abelian extensions of K, then their norm, the image norm of L1 is not the same as norm of L2. So okay, well, of course, by Galois theory, if they're different extensions, different Galois extensions, then their absolute Galois groups are different. Okay, so or even their billion Galois groups are different, right? Just using the Galois correspondence from K-ab down to L. And so each one of these guys, so what do I have? I have two different open subgroups of odd of K-ab over K. Okay, so that's what if the extensions are different, then their corresponding open subgroups are different. So after interchanging them, if possible, there must be some element. There must be an element that's in one of them and not the other. Okay, and if you think about it for a second, then possibly after interchanging L1 and L2, one of these one group set minus the other group has to be non-empty. Each one of these groups is opened and also closed, right? Which is really cool. Open subgroups are closed. And so therefore this complement is also open, right? So this guy is open and then the complement, minus is intersecting with the complement, which is also open because the second one was also closed. So the difference here is a non-empty open subset of K star, but we know that the image of K star under the reciprocity map is dense. That was actually kind of obvious from the fact that it was surjective at every finite level. Well, so if it's dense, what does that mean? It means that there exists an element which lands in whatever open set that I want. So there exists an element that lands in U. Well, what does that mean? That means that I have an automorphism that fixes L1 pointwise and doesn't fix L2 pointwise. But moreover, this guy is this guy is the kernel of of the map from K-ab, of the kernel of the map from odd K-ab over K to odd L1 over K. And so if you, as an automorphism of L1, Wx is trivial. Therefore, X is a norm from L1. That's the correspondence that we have. On the other hand, as an automorphism of L2, Wx is non-trivial. Therefore, X is not a norm from L2. Okay. Right, again, just using the basic fact that at any finite level, the reciprocity map of L over K induces an isomorphism from K modulo norm of L down to the automorphism. Okay, and so I think I'm done because I found an element that was in one of these norm groups and not in the other group. Okay, so that's just kind of some Galois theory. And so yeah, let me really touch up the Galois theory here. So if I have a finite abelian extension, then the reciprocity map and its inverse induces a Galois correspondence between open subgroups of K star that contain an L star, which itself is open. We just proved that, and sub-extensions M of L over K. What do I mean by Galois correspondence? I mean, whatever anyone ever means. This is inclusion reversing, right? If you think about it, the biggest open subgroup is K star, and so I'm taking the thing to the to the norms, and so I guess it's easier to say what it is the other way. So if I start with K itself and I take the norm, K is the smallest one, I take the norms from K, well then I get K star, and that was the biggest that was the biggest open subgroup of K. If I take L, then I get norm of L. Yeah, so this is a anti-isomorphism from the lattice of open subgroups of K star containing L star to the lattice of sub-extensions. Okay. Just like in usual Galois theory, there'd be an isomorphism from this to to subgroups of L over K, which of course is kind of what it is, because each one of these is also isomorphic to the automorphism group of L over K. Okay. So what's the point of this? In particular, if you think about this, what am I saying? I'm saying in particular that any subgroup that contains a norm subgroup is also the norm subgroup of a sub-extension. That's really what I'm saying. Okay, so the proof is not hard at all. So for every sub-extension M, every sub-extension of a finite abelian extension is, of course, a finite abelian extension. So by what we proved, we get an open subgroup. And again, how do norms work? The norm group from a bigger extension is going to be contained in the norm subgroup of the smaller extension. And I've written that in the correct order here, because L is bigger than M. Okay, so for sure, this omega inverse map that associates to every sub-extension a norm subgroup that contains an open subgroup that contains NL star. And we just saw that this correspondence is injective. We saw that it was injective overall among finite degree abelian extensions. So if I want to restrict to finite degree abelian sub-extensions of my fixed finite abelian extension, it's the restriction of something injective, so it's even more injective, probably the same amount. Okay, and so now what do I know? Of course I know that K star mod NL star is isomorphic to the automorphism group. So I have this injective correspondence from subfields into subgroups. And so what do and so the only thing what am I still trying to show? I'm trying to show that this correspondence is surjective. Right, so I'm trying to show that every subgroup of K star containing norm of L star is the norm of M for some M, and that's just going to follow from an immediate counting argument at this point, because by Galois theory, the number of sub-extensions M is equal to the number of subgroups of the automorphism group of L over K, but the automorphism group of L over K is isomorphic to K star mod L star. So the number of M's is equal to the total number of subgroups, and the correspondence that associates M goes to norm of M is injective. So I have exactly the right number of subgroups, and so every such subgroup has to be a norm. Okay, and so that ends the Galois correspondence there, and then let me just tell you where we are at this point. Okay. So we can certainly define a map from the profinite completion of K star into the maximal abelian extension of K, right? That's the way the profinite completion works. Every continuous homomorphism from a topological group into a profinite group factors through the profinite completion. So we have such a thing. The point, we know it's surjective because K star is because already the image of K star was dense in the Galois group. If you think about that for a little while, that implies that once you extend to the profinite completion, the image of the profinite completion should be dense and closed. So it should be the whole thing. And so the real problem here is that we might have a kernel. Okay, so let script dk be the kernel of this map on the profinite completion. And so what's happening? What is this kernel, right? If you think about what's going on, then I can identify the kernel with the intersection over all the norm subgroups of the finite abelian extensions. Here, what am I doing? Here, I'm using the fact that there's a bijective correspondence between finite index open subgroups of your topological group and finite index open subgroups of its profinite completion. That's kind of exactly what profinite completion does. So I can think of these norm subgroups as being they're going to map under the map from the group to its profinite completion. They're going to map homeomorphically. Okay, and so so that's the problem. If you think about what's happening here, we have a surjective homomorphism on the profinite completion, and the kernel is the intersection of all the norm subgroups of the finite Galois extensions, which we already saw is the same as the norm subgroups of the finite abelian extensions. So the real existence theorem here, that's what it's called, the existence theorem. We need to have enough finite abelian extensions of K so that when you intersect over all the norm subgroups, you get the trivial group. Then this profinite complete. Then this map will be an isomorphism. Okay, so that's what's left. Everything else is done. Okay, well, that's it for today. So, any final questions? Okay, well, yeah. So I think I think in chapter 9, Harari proves the existence theorem in characteristic 0, not very difficult. Oh, the next thing that's coming up are local symbols, which are kind of fun. And so using local symbols, then he'll prove the existence theorem in characteristic 0. And then I think we switch to Lubin-Tate stuff, which is a more elegant kind of approach. And then the Lubin-Tate stuff will, in particular, will prove the existence theorem in positive characteristic as well. That's characteristic 0. And then I don't know. I think maybe in a couple weeks we might move on to global classical theory. All right. See ya.